I don't know if I'm just going to skip over whole sections because that means I'd probably have to do a slide about every 30 seconds, and that might be just a bit too fast. Quick introduction, my name is Hoglund. I'm probably most well known for my work on the rootkit.com site and stuff related to rootkits. A couple years ago, I started a company called Senzik, and I worked for about 3 years on a product called Hailstorm, which is a fault injector for the network, black box injection style. I've since graduated from that thinking process, and I'm trying to integrate a whole bunch of different concepts into a single cohesive process for finding bugs in software. So I call this the GreyBox process. Some of you may have been to the E&Y booth over there. I noticed they were talking about GreyBox, and I actually am not in cahoots with them. I went over and asked them their definition, and fortunately it's pretty close to mine, so there won't be any confusion there. Now I have a new company. I've since left Senzik. My new company is called HB Gary. And what we do is we exploit software. The whole point of this company is to develop survivable payloads that work in the field and that they're dependable in nature. And so part of that process is, of course, finding bugs, ODay, or testing bugs, testing exploits against a variety of targets. So this is obviously something of value for me, but I don't think there's a product here. All the stuff I'm going to show you for the most part is stuff that we're going to be releasing for free or have released for free off the website. The reason why is that people who are reverse engineering software, there aren't very many of you out there. There's not enough of you to validate having a product, so it's going to be basically all free. And of course, this is something you shouldn't trivialize. The process is taking what's otherwise a black art and making it something that's repeatable and consistent. And overall, that's going to save you a crap load of money if you're developing exploits, which I know is something that a lot of people are doing. Now, the fun part of this is that I'm a deconstructionist. Many of you probably are too. And that means that you really like to take things apart. I'd much rather take something apart than build it. And there's something about this secret knowledge of having some kind of ODay or other thing that appeals to our deep psyche. And this is an age-old battle, which probably goes back to the days when people invented crypto and secret messages were passed around, and then other people figured out how to decipher the crypto, the ciphers and the codes, and took it apart. And this battle still goes on today. Now, there's a much better reason, a much more concrete reason to be looking for ODay or trying to exploit software. Exploits are worth cold, hard cash, plain and simple. I think it's ridiculous, some of the people in the community who sell their exploits to iDefense for $50. A vulnerability could be worth 6 figures, easy. Think about what a remote ODay in Cisco would be like in the hands of a drug cartel or in the hands of the military. And if nobody else knew about it, think about how powerful that is. From the software vendor's point of view, it's easy to see over 100K value in an exploit because that's about how much it's going to cost a large software vendor to fix a bug if it goes into deployment and everybody finds out about it and they have to deal with the PR cost of that. The other thing is that exploits are worth lives. If we have an exploit that works from remote, we have this concept of standoff now. We can do something that may have required a physical penetration before, which means that we aren't putting a soldier's life in danger. And exploits are obviously strategic, because if you can get something into a computational systems are used to make decisions. And if you can change the way those decisions are being made, you get ahead of your enemy's decision cycle, and that's exactly the point of information operations. Now, exploits don't last long. Their survivability depends on nobody else knowing about them. If somebody does know about it, they can obviously patch against it or detect it. As soon as you use a new exploit, the very moment you do it, you run the risk of compromising that asset because the person you just attacked may sniff that and be aware of it. So that means that there's a time between when you have a new weapon and when that weapon is probably not going to be as useful. The other thing is that if you're doing this in a lab, the public may find that same vulnerability, and alternatively, your enemy may find the same vulnerability, and thus the value of that goes down. So this is the mission statement. In order to maintain a battle advantage, your offensive information capabilities must include a lab process for finding and exploiting new software bugs. That is a constant, ongoing process. So, I broke the talk in a couple chapters. The first one's the bugs. I'm then going to talk about some of the tools that we have, and towards the end of the talk, I'll show some pretty pictures. So, chapter 1, the bugs. I have 4 classifications of these. The The biggest one, of course, everybody's aware of is buffer overflows, lack of balance checking, or arithmetic errors causing these. A more obscure but equally powerful attack is parsing problems. Now, this is a new area. Buffer overflows, by the way, are going to go away pretty soon. Probably give it the next 5 to 10 years, and you're not going to see too many of these out there anymore. You can already see it. Many pieces of software are not vulnerable to simple buffer overflows that previously were. Parsing problems are interesting. General state corruption is just kind of a more general problem of the parsing problem, and then race conditions. So obviously this is old news. Everybody's talked about buffer overflows to death. I think the only point I'm trying to make here is that they're still common, but they're going away rapidly as compiler technologies are being upgraded to get rid of this issue. Microsoft, I think, will be producing the most secure code in the entire industry within 5 years. So, parsing problems. Let's move on to something more interesting. They are not solved by better compilers. Rather, they're solved by having good algorithms. And most human beings are not very good at designing good algorithms. So there's this idea I had that maybe if someone built some standards for algorithms, we would have some peer review on that, similar to crypto, and these things would get better. But the fact is, I don't think this is ever really going to happen because people don't really like standards and everybody makes exceptions to the rules. So I think for a long time, we're going to be looking at parsing issues. General state is just a different term I use. It's more general for the same issue. You have a set of states in the target computer. There are many more states there than the builders of that system intended to be there. Think about it, emergent states, right? There could be potentially thousands or millions of possible states in a given application. Do you think that the programmers who wrote that were considering all those possibilities when they wrote it? Oh, no, they weren't at all. What they were doing is running their compiler over and over again until all the errors went away. And as soon as that happens, they ship it over to QA. And if QA doesn't find any problems, it's out. And QA, in most places, they're not very good. So general state exploits would be a situation where I can send a set of commands in exactly the right order, thus manipulating the state of the target machine into an insecure state, and thus performing an exploit at that point. Now, this could be solved by using provably correct systems. Now, that's a very old idea. But how many of you have actually seen a provably correct system? Has anybody here ever seen a system built? If you have you seen how much it costs to build a system like that? And once it was built, how long was it actually used in the field before it was replaced by newer and better technology? I think you get my point. Race conditions are the buffer overflow of the future, in my opinion. We're going to have more distribution of agents and other things that have to stay in contact with each other and stay synchronized. So I'm not going to talk too much more about race conditions in this talk, but it's the type of thing that I smell a lot of potential for exploits in the future. When we have a lot of different nodes that have to communicate, it's very easy, obviously, for them to get desynchronized from one another. All right, so now I'm going to talk about GreyBox. I'm actually going to give you a little history of the different testing methodologies that are out there. I'm not going to belabor them too much because I'm sure most of you know all this, so I'll go quickly through these slides. But quick definition here, GreyBox is to combine a set of tools, including, first and foremost, static analysis, and then augment that with runtime analysis to correct your data set. Static analysis is not going to answer all the questions that need to be answered about the software, and thus at runtime you can gather additional data and augment your data set and learn things that you otherwise would not have been able to see. So Whitebox is, in theory, operating with full knowledge of the system. Anybody who's read source code or looked at binary analysis knows that's a load of crap. Even though we call it Whitebox, we have no idea what the intent of the builder of that system was. We get a tiny little sliver of what they were looking at. Obviously, we have tools like IDA Pro that help us with this. The term used is dead listings, typically, when we have a disassembly. And I think that source code, in this case, is just merely documentation for the binary itself. Very good documentation, mind you, but we're concerned about the binary. The most important thing is we're not actually executing the software. So in our process that we're still developing, our GreyBox process, the first thing we do is we run it through a product that we have built called BugScan. And we immediately obtain, like instantly, a quick report of how bad the situation is. Schematically identifiable vulnerabilities are put into a report. We can scan a whole bunch of binaries up front and figure out where we're going to prioritize ourselves. If this one over here has a bunch of really good coding practices going on, and this one over here has a bunch of bad ones, we know where we can, put the muscle. Now, if we're actually going to go further than just looking at the binary, we're going to obviously do an IDA dead listing of that. And IDA is the best program out there for managing dead listings, because it allows you to comment them, cross-reference, jump all around. It's not the fastest decompiler. I can put something in IDA and it'll decompile in maybe 3 or 4 minutes. Same program in PEDASM will disassemble in something like 30 seconds. And it has full cross-referencing as well. So even though IDA is not the fastest disassembler, it's certainly the easiest to use. Now, static analysis is never going to answer this question. You can't say that something is exploitable until you exploit it. So obviously we've got to go further than just looking at dead listings. Every automatic analysis tool has this problem, and you cannot remove the human auditor from the loop. The human mind is the best pattern matching system we have. But unfortunately, we are expensive and slow. So what I found is that we spend a lot of time as an auditor doing things that are tedious and mundane, like writing down hex addresses on a napkin late at night. This stuff needs to be automated, and so that's where I'm approaching this from. I'm not trying to build a magic tool that solves all our problems. I'm trying to make tools that allow the auditor to stay in the zone. Don't get out of the source code to go do this other thing that's completely meaningless, to my thinking process. Another thing to note about static analysis, and I think this is important, even if you don't take the time to actually find an exploit, you got to ask yourself, does it matter? What if I do have a sprintf or a stir copy in there, and this particular interface isn't exposed to any user supplied data from the network, but it's in a DLL? What can I say about the developers that are going to be working at this company 10 years from now? Absolutely nothing. They may reuse that in a different module, expose it suddenly. So by that token, I think it's valuable to consider that every possible vulnerability is important enough to warrant it being fixed if you're on the defensive side. Now, automatic bug detection requires a schematic for what that vulnerability looks like. So things that are easy to detect schematically are signed to unsigned conversion errors, bad API calls, format string buffer overflows. This is effective if we can get IDA or our disassembler to find all the instructions. This isn't always possible. And there's all kinds of little issues that come up, like calling to registers or having these undocumented structures that obviously you're not going to know unless you run the program and look at it. Pure static analysis is not going to answer these questions. Many branching decisions are made based upon user supplied data. Every time you see a compare followed by a jump if not equal or a jump if larger than, these things, these are influenceable by the user. So we want to track where all the branching decisions are being made. This helps us increase our code coverage. If we're doing a test, we want to increase the code coverage as much as possible because every branch, there could be a potential for a problem in there. Now, for a static analyzer to do this, it has to emulate execution. At some point, I posit that any emulation of the execution is equal to just simply running the program to begin with. Another issue that I've run into a lot is when I'm backtracing. If I'm backtracing data, I often run into, I call them runouts. We'll go back a certain distance, and there won't be any locations cross-referenced to me, but I know something's there. This happens, for example, with message handlers in Windows. So this is another issue that we run into doing static analysis, that if we had runtime analysis, is almost instantly solved. Now, black box. If we're going to do runtime analysis, we have to be able to exercise the software. For most software, it's going to be more difficult than just telnetting to the port or sending things via netcat. As many of you have probably realized, clients and servers maintain state with one another, and client code can be very complex. I learned this when I was working with Hailstorm, and I was trying to model some very complex protocols, Samba being one of them. Do you realize how difficult it is to build Samba packets and maintain state completely from scratch? It's hard. And it's very difficult for someone who's not familiar with protocols to get any kind of value out of that because they're not going to be able to build those protocol models themselves. Now, some fuzzers I mentioned in Hailstorm, there's one that's very good from Dave Itel, Spike. You're going to need something. And to do this fuzzing from a tool like this, you're going to require deep protocol knowledge. Black box has a couple of disadvantages. When you're doing input injection, it can take a great deal of time to complete a sequence. I've run black box injection against a target overnight, come in the next morning, it's still running. That happens. If the program is running slow, that obviously compounds it. This is just a brute forcing problem. And unfortunately, most of the black box stuff that I've been exposed to doesn't get very deep code coverage. It just gets in just a tiny bit, maybe 1 or 2% into where it's receiving. But it does work. As this screenshot illustrates, this is something I did last year. I'm running Hailstorm against Microsoft SQL Server, and I'm just changing literally random data into a field. I mean, this is as simple as it gets, and we get a buffer overflow. Now, it's really cool because I'm actually running Rational Purify on the binary as I'm doing this. And you can see in Rational Purify the actual addresses that are having memory corruption. So using black box in conjunction with an instrumentation of the target, which is what Purify does. Matt, what's the name of that one? Valgrind? Valgrind for Linux does the same thing. You will get actual code addresses where corruption is occurring, and that helps a lot, especially if you're on the offensive side. Now, I just talked about this, so I'm not going to talk about it again. Now, one of the cool techniques that I've been working on lately is just instrumenting clients. So one of the targets that I've been analyzing is Microsoft SQL Server, and it accepts connections over port 1433, and I didn't want to build those transactions by hand, so there's this really cool program called FreeTDS. Well, FreeTDS is open source, so it's very easy for me to go and add additional code to the client to make it hostile, to mutate it. And so this is a very effective way to target an executable. And don't make the mistake of thinking you can't have a client. You're going to need some kind of client that allows you to mutate the transactions. You could man in the middle of the packets. I know some of you are thinking about that, but think about when you have an authentication sequence and then your post-authentication and now it's all encrypted. Man in the middle on the packet doesn't really work very well anymore. If you don't have the source code to your client, you can hook the client. This is a possibility. You can just put a breakpoint on a location and swap a memory pointer to a different memory pointer. If the buffer that you're playing around with is not going to change in size, you can just write over the existing memory and just change some values there. That works as well. Using a debugger, I mean, it's simple technology. Now, GreyBox is combining these tools together. If you use a program debugger, you're already to some extent performing GreyBox analysis. Now, obviously we're doing this at runtime, so we can observe everything about the target. Every single instruction which is executed, we can observe. And we can trace data, and that's more important than anything. It's obviously a very interactive process. This is something where you're going to be sitting there, or the practitioner is going to be sitting there working with this thing, resetting the state of the program, changing some value, walking forward, seeing what happens. Again, the human pattern matching system is back online and getting what it needs. So there's a whole list of tools there that are used. Now, all the stuff that I've been working on is all Windows-based, and so I think it's worth mentioning Fenris at this point because it just does a lot of the stuff that I'm talking about, and it does it for Linux. And this is going to be obtained somewhere through a link off BindView. Now I'm going to talk about BugScan very briefly. This is the only thing that I have that's actually a product. The rest of the stuff is all tools. The key here, the biggest thing I learned when I was building Hailstorm is that you can't make a product really complicated. So the coolest thing about BugScan is that it's extremely simple to use. You put the binary in, you get the report out. It doesn't tell you if it's exploitable, of course. It just gives you a hint of where the locations might be. But it takes 30 seconds, not 30 hours, to do this work. Scalability. Now, so here's how it works. It has a web interface. You submit the binary, hit upload, get the report. Oh, wait, did you miss that? Let me go back. Submit the binary, get the report. Now, the report items are pretty cool. They're red, yellow, green. Yellow is like a coding error. Red is like we believe this to possibly take user input from the network or something to that effect. And a green is actually a reward. If we see a good coding practice, like an strn copy, for example, it would be marked green. Now, I have a couple of reports I'm going to show you. I cannot tell you the vendors for these products, so don't ask. But I'm going to show you some reports in the field. For this particular talk, I did different targets for my last talk, the one I gave in Amsterdam. This one, I'm just going to have a couple of SQL servers up here. Here's one of them, where the number of SW printfs number is close to 400. There's 200 sprintfs. These are all by the way, API calls, which are no-nos per the book, writing secure code, a required reading at Microsoft. That's a quote from Bill Gates. It's on the cover of the book. Now, this looks kind of bad, right? These are big numbers here. I'm about to show you something that's going to blow your socks off. This is so bad. This is another leading database. This one, by the way, is unbreakable. I'm not going to say any more about that. Now, let's say I had run an analysis like this, and I got some really good information. Now, I actually want to use it right off the bat. Here's something I can do right off the bat in my lab if I want to find an exploit. I call this red pointing. I take all the memory locations where I found a suspect location, and I drop a breakpoint on them, and I run the target. I mean, this is taking me 5 minutes, and it's very simple to do. It's obviously going to only catch a very low-hanging fruit. So for this example, I downloaded a proxy server like 2 days ago from 2cows. I know it's cheating, but whatever. So here in Ollie debug, I'm going to take Control-G, type in lstir copy A, I'm going to set a breakpoint right there. Very simple to do. On the Allegro Surf proxy server, I tell that in, and I say I want to connect to this host called foosball, and what happens immediately? Boom, I hit a breakpoint, and look at the little stack trace there. lstir copy A, you see it? And my user supply data is being used there. Just like that. Okay? Now, this tool that I just showed you, BugScan, you can all use it for free. Go to this website. If you were at Black Hat, and you can tell us who you are and stuff, we'll give you a 60-day free use. We have it online, so you can try it. Put anything you want in there, see what you can find. It's a lot of fun. It's actually, I'll warn you, it's very addictive. You'll be like, oh, I found some problems in this. That was pretty interesting. Okay, I'll try this other thing. Boy, that's really bad. I'll bet you this other thing's a piece of shit, too. Put that in there. Okay. Did everybody get a chance to see that? It's in the printed materials, I think so. All right. Now let's talk about some more real-world stuff with what we're doing in the lab with our GreyBox things. Now, all this technology we're releasing for free off the website as we polish it up. Now, the reason why I call it hard stuff is not... Mostly experts are just going to be the people to use this. These are people who have skills in runtime debugging. They know what assembly looks like. They know how to read assembly code. They have experience dealing with protocols, and they have technical knowledge of what programming bugs look like. So for most of you, that means you've sat down and tried to find bugs in software before, and you actually can get around in there a little bit. So an example of how you might use this is a parsing problem. Since I was on proxy server page at 2cows, I downloaded a couple of them, and I found a problem in a different one. So let's say we have a target, sprintf, and we want to see if we can get in there. And we get into IDA, and we see a couple of locations here. We see a branching decision being made based upon the result of a stir cur. Now, if you note my little comment up there, I happen to notice that the argument to stir cur at runtime was being pushed hex 23, which is a hash sign. So I know that a hash sign controls whether or not I branch here. And so it was very easy for me, once I did the runtime analysis and saw what the actual value was, to go down and actually, for the POP3 proxy here, put a hash sign in there. Okay, very easy. And I did actually then go down the branch and hit the sprintf, and look what happens. Both pieces of, let me show back, we'll go back one here. Notice I have Hoglund and then £, and then my web address up there. Okay, so going down here, both of those strings are getting pasted in with %s with a sprintf here. So yeah, and you can see the result. The very top line is actually the final string. So obviously we can make overly large strings here as well. Now, I have a code named Tempest. I've lately been known to come up with really horrible code names for things. Tempest being one of them, considering it's already used for something else. So there's the website. You can download some of this stuff. I've also created 2 SourceForge projects for Restart and SpeedBreak, 2 other tools. And hopefully I'll do more SourceForge projects as we get the stuff polished. So the whole point of this exercise is to connect your inputs with the bugs. User supplied input over here, possible bug over here. I want to make sure I can get the user input all the way down over there. Obviously they can help you verify an exploit, build a working exploit. This is an offensive stance. More importantly, this goes back to the workflow. The stuff I'm working on is about a workflow, and that helps you get more stuff done faster and helps you scale up your operation. So here's a screenshot of something from Tempest. This is a static analysis at this point. I haven't done any runtime analysis. These are code locations that are branching. Down there where you see the red around the square, that's a sprintf call. And then up above it are all the code locations as far as control flow is concerned that lead up to this printf possibly. Now what I'll do is I'll paint those locations as I instrument the target and run with it. Now my eventual goal is to have this be self-learning. If I see a branching location, a branch decision based upon user supply data, I'd like to be able to stop the program, change the value, and rerun it from that point forward. So we actually started doing that. We have a program called Restart, and that's one of them that's on SourceForge. It is the coolest thing you've ever seen. We can freeze a program, we can read all the process memory, store it off, and then as it turns out, if you restore that process memory at any time in the future, it restores the program back to its original state. I actually ran it on Winamp. So I have this really cool techno stream going. I freeze it in Restart, and then I let it go again, so it's going, and then like hit Restart, and it's like resetting itself over and over again. So I'm like remixing. I'm not GreyBoxing, I'm beatboxing. Keith made me do that. Okay, so how do we actually measure the code locations while we're running? So we take each of the code locations and set a breakpoint at the top. This was a trick that Halvar gave me about 2 years ago, and I've been using it. It's very nice. So we just insert a CC for x86 in here, and we have a breakpoint. And then this is what I was just describing, the process snapshots. So we actually read using virtual query EX, and there's a variety of flags that have to be set, and you'll see them listed on the side there. And we go through the whole process space from 0 to top, and we grab anything we can and save it off. So moving on, flybys and drill downs, that's what we're going to get when we start using this technology. We'll see that we hit a code block above a potential location. That's a flyby. We want to hit it. So that's the drill down. Now, for a code flow, for tracing the data, you can see here I've selected, my color scheme's a little weird, but I've selected the block on the bottom, and I can see everywhere where it branches to. And that's kind of neat. The graphs can get a little complicated. Here's a better example, actually. Trillion IRC DLL. I have assigned to unsigned mismatch on the bottom, and up on top I've selected it. And this is actually, you can tell right off the bat, for me, using this, I can tell that's a switch statement. All those locations are all the cases of the switch statement. And so I select it, and I can see which items on the case statement are going to lead down to the signed to unsigned mismatch. Now here's another trick that I came up with that we've been using, boron tagging. Let's say that we don't want to actually single-step trace from a WSA received from all the way through the code. Rather, we just pick a string, let's say it's rootkit or something, and we type that into our request that we're sending to the client. Great. Goes in, let it process, stop, break into Ollie debug, scan memory. Ollie debug has a great memory search function. Scan all the way through memory, find the locations that still have that string in it that you just typed in. You can do the same thing with soft dice. If you do a search, by the way, for like, let's say rootkit, put in something like rootkit 666, because sometimes you'll hit the location that just took your command. You don't want it, you want to tell the difference. So anyways, you'll scan through, you set a breakpoint on those memory locations, and the next time they're read from or written to, you get a breakpoint, and you're right in the code that's dealing with user supplied data. It works really well. Unfortunately, it doesn't work all the time. One of the times where it wouldn't work is if that memory is cleared shortly after you run the request, and that does happen occasionally. Other times, it may be different memory altogether that's being used, so you don't hit the breakpoint. So here's kind of how it would work. Let's say we're going to leapfrog. Every single time the memory is written to or read from, for the boron tag was, we're going to leapfrog. We're going to see each location and then just let it run again. Leapfrog to the next time it does it, and then the next time that it does it, and so forth. We're going to end up with these little clusters of code graph. They won't be connected, but that's okay. So there's a call to receive, writes memory out here. Now we change the page protection on this page of memory, so that it'll cause an exception whenever there's any read or write event to it. And then in each single time we have any event against this particular location, we can cross-reference against the address and the length of the buffer and determine if it's against our user supplied data. So that's boron tagging. Unfortunately, with Ollie, you can only set one at a time. And so I'm working on a tool to put like multiples in there. The next big goal, by the way, is data flow analysis. I don't have a really good tool yet, so there's nothing released on this. But the idea behind data flow analysis is, obviously, with the tools I already showed you, I can detect when someone reads a piece of memory. are writes to it. So by that token, I should be able to follow that memory as it propagates forward. There should not be any point in the control flow where I wouldn't be able to determine if the data flow, if the data in question is being moved somewhere else or copied or any of that. So I should be able to roll all the way forward and do complete data flow analysis at runtime. Here is a prototype for that. I actually wrote some code here shortly before I gave the RSA version of this presentation. This is a real data flow using that kind of concept I just showed you here. On the left-hand side are registers, and on the right-hand side is either stack or heap memory. And I'm actually tracing, I use a supplied piece of data forward. Now, unfortunately, you see how it goes off the bottom of the screen? It goes off the bottom of the screen like to China. So that's a problem that still needs to be solved. Now, talking about these kinds of things, graphing can be a problem too. I showed you some cool graphs, but to be honest, I searched for some really pretty ones. Most of my graphs right now are ugly as sin. There's millions of things just pasted on top of each other, and so that's still a problem I'm trying to solve. Graph complexity is a hard problem. So I've come up with a couple things I was playing around with. Hyperbolic trees is one of them. This is actually all the locations in an FTP server that I have leading up to a possibly vulnerable sprintf location. You can grab this globe, it's rendered in OpenGL, and turn it. It's really cool. But the thing is, it's like, what happens if you have something that's a little bit more complex than this? Don't make the mistake of thinking hyperbolic graphing is going to solve every possible control flow in an application. It looks pretty, my friends, but it's completely useless. Oops, sorry. You can download this tool. It's called Walrus off of the address listed there. Now, in terms of getting rid of extra stuff in the data set, obviously we want to filter out stuff we don't care about. Let's not look at sprintfs that don't contain a %s in them. If the off by one error that we detected is smaller than the stack size we're dealing with, and we know that, we obviously aren't going to look at it. So we're just talking about, we just got to have good filters to get past a lot of the stuff up front. So I'm going to reiterate some of the things I just showed you, how the processor would work. The first thing we'll do is ID locations in the code using static analysis and perform static traces. You can see that data there. Then we'll fuzz the inputs while measuring, instrumenting the target. And here I'm painting every square that's painted gray I've visited, using that's the breakpoint trick. And so my goal is to get down to the location, and you can see I actually hit it there. This is really cool. This is part of Tempest. All the potential vulnerable locations are listed on the left there in this UI, and I can actually assign each of these to an engineer. It actually has like a problem tracking system built into it. So believe me, when you do this, you'll have, like the previous example, 2,900 and some odd locations you want to analyze. Forget it. If you don't have a tool like this to tell you where you are in the whole thing, you're going to get totally swamped. You're going to get disheartened. You know, like, how much work do I have left to do? And that can be the killer. So here, you know, I can assign 100 of these things to one guy, 100 to another guy, and they can actually set values on there, like it's assigned, location not exploitable, location visited, unknown if exploitable, and so forth, and you can close out each of these potential locations over time. That's so valuable. It's more valuable than having the O-day, okay? Now here's an example of something in the last talk where I actually, using Tempest, was able to find a bug really fast. So there's an FTP server called Black Moon. In the previous talk, I didn't say who the vendor was here, but it's one of those 2 cows programs, so I don't really care. The pre-authentication, I just enter your username. All right, so I put in my username, and I'm seeing in Tempest a runtime sampling of the data as it's going past. I immediately see these select statements that have my username in them. They're using a database to tell if you're, you know, obviously a correct user. And so I think this is a really funny example because it's a SQL injection attack, but something that's not the web. This is so cool. I mean, this is GreyBox working for you. It took me no time at all to find this problem. So, were there any faults? Okay. If there are faults or things that are interesting, we can annotate that particular line. So that one maybe is assigned to my engineer, John. And John writes in there that, you know, hey, look, it looks like there's a select statement, blah, blah, blah. And now you can leave that alone and keep working, and we can come back to it. So annotations are very helpful. Now, this is step 2. How many of the branches remain unresolved? So in this graph, I've colored it differently. Orange locations are conditional branches where we've only exercised one side of the branch. Jump if not equal, only one side went this way. So we know that potentially we can increase our code coverage here at this point. So we can go look at the assembly language at that point and determine how it is that it's making that decision. Is it making it on a compare against user supply data? If so, we can control that and we can increase our code coverage. In this particular example, if the locations are surrounded in green, user supply data is actually being used in that particular location of code. So our data flow analysis is at user control, blah, blah, blah. Modify our input fuzzer to compensate for that problem. That's the self-learning code coverage I just talked about. So in this example here, I would go to the nearest flyby, that's the grayed out location up above, and I'd attempt a drill down based upon user supply data and watching what's happening and forcing the branching to continue down that tree. Not all control flows as identified by IDA are going to be even exercisable. Sometimes there's just things that will never happen because there's some global state or something that's being checked. You can't control it from a user supplied variable. Maybe it's a configuration setting that changes the way that works. Anyways, enough said about that. So I've ripped through this. Hope I didn't finish too early. The conclusion of this is that there's a process by which you can connect user supplied input with the target locations in the code. You can trace your data and control flow at runtime to do this, and you can tune your fuzzer to increase your code coverage. Only a certain percentage of the bugs that you attempt to do this with are actually going to be exploitable, of course. In fact, it's a very small percentage. There's my website where you can get both bug scan and some of the tools that I've been talking about, and here's Dave Itel's site for Spike. You can go download that as well. The tempest stuff is something we're just using internally. It's not a commercial product, so don't call us for tech support. Thank you very much. I take some questions. Yes, sir.
The restart program only available in Windows?
The question is the restart program only available in Windows? The one that I have written is only for Windows, but the concept of how it works is equally applicable to any other, like Linux, for example. I'm not familiar with that. Anybody else? Yes, sir.
Do you think there's any chance that the work that hardware uses to create test vectors or vector design or hardware service automated?
Do you mean the same algorithms or the tools they're actually using?
Yeah, sort of the algorithms.
The question was, if I got it right, would the algorithms being used in hardware testing be applicable here? And I think there's a lot of prior work in this area that I myself haven't even had the chance to research. I just started on this stuff. I think that anything in the testing arena that, from an algorithm point of view, especially with hardware and stuff like that, would probably be valuable, maybe to be integrated here. It depends. I mean, some of this stuff is just so weird that you run into, and it's hard to say anything about it up ahead of time until you actually see it, you know what I mean? Yes, sir.
Run into any problems when you do local executions with memory being allocated to a different address or the DLLs being located in different addresses like that? It's screwed up when you're tracking across different runs?
Okay, so the question was, will variations in the way memory might be allocated or such where a DLL may be remapped to going to cause any problems with multiple runs? I'm not correlating multiple runs currently, so I haven't had a chance to run into that problem. I will say that with Ollie debug, it doesn't have any problem finding it even if it's been rebased, so you're not going to run into it as a problem for finding the breakpoints to begin with. However, if you collect the breakpoints and you store them off as addresses and then just restore those addresses, you most certainly would run into a problem if it was rebased. The breakpoints would end up in the wrong locations. Anybody else? Yes, sir. The question is, how does restart deal with open file handles and whatnot? Well, I'll restate the question as, how would restart deal with any external data outside of the problem? It doesn't. It doesn't. And that's obviously a problem. You could try snapshotting other things, but at some point it just becomes a real hard problem to try to capture the state in the system as it gets too big. Anybody else? Yes, sir. Have I sold many exploits? I cannot comment on any of that work. I'm sorry. Anybody else? Oh, sorry. Podium's.
So the little graph there where the boxes were gray,
Yes?
and it led to a red location. I noticed that there was like gray, gray, white, gray, gray. If, like there's a white in the middle that hasn't been visited, but there's no other links to the, around it, sort of, how did that happen?
Okay, so let's say the question is, there's a control flow that's mapped, and I've got gray down below and gray up above, and a white in the middle, which means not visited. The answer to that is that's some sort of bug in Tempest. It most certainly should visit that location on its way down there. It may not be a bug in Tempest, it may just simply be the initial white box analysis didn't resolve that control branch, and so it was never able to be graphed to begin with. There is a way to fix that, is to map additional control flow at runtime. Now the current way that Tempest is implemented is it takes the control flow from the static analysis and just augments that data set. It doesn't add additional branches on the fly. I think that would solve the problem. You had a, yes sir. I'll get to you.
What are the accuracy rates for bug scan? At least for the hits.
What are the accuracy rates for bug scan? Well, if bug scan says that there's a location there that matches one of our schematic patterns, then it's 100% accurate. But of course, bug scan's not going to be able to tell you if user supply data is being used in that location, and it's certainly not going to be able to tell you if it's exploitable. But it's going to tell you a lot more than you would know without having to get into like an IDA disassembler or something just on your own. And because you can submit files to it in huge batches and queue them up, you can get a lot of work done overnight and come in the morning and sort through a big pile of reports and do something fun with that. Sir, you had a question?
How important if you run against encrypted binaries and something out of Zillow?
The question is, have we run against encrypted binaries? At this point in time, I haven't tried to use any of the runtime stuff against code that is self-decrypting. Now, I think that's an interesting question because I think runtime analysis would be the only situation where you'd even be able to get a handle on something like that. So it would obviously be a really hard challenge, but you're obviously not going to get anywhere with it from a static analysis point of view unless you have some magic plugin that knows how to reverse the trick that's being performed there. Yes, Ryan?
I have essentially the same question.
Okay.
The comment I would make is that what I think we want to do is actually get it to an unpacked state and start to satisfy it.
Right. Okay, so Ryan's pointing out a very common method to deal with this problem is you get it to an unpacked state prior to doing the analysis. And there's tools out there for many of the packers, there's many unpackers. You just got to find one that works. Yes, sir. Oh, absolutely not. So the question was, what kinds of binary files will BugScan support? And if something comes up from the demo account, would we report anything based on that? Absolutely not. We would never report anything based on that. The analysis BugScan engine can deal with a lot of different hardware platforms. But currently in the marketing literature, we're only saying C and C++ code written for Linux and Windows. Now, C and C++ code is even a little bit misleading because we're not analyzing source code, we're analyzing binaries. But the patterns we're looking for are based on libc and other things that would be used if you were using a C compiler. So at this point, C and C++, Linux, Windows. You can throw ELF in there, you can throw Spark code, you can throw AIX code in there, you can do all kinds of things. We just don't make any promises about what you'll find that's not currently supported, but it'll actually create a report and you can see what it looks like. Yes, sir. Well, so the question is, what do the schematics for BugScan look like? Boy, I wish my product guy Matt was up here now. First of all, look for imported function calls that are known to be poor programming practice. And it will look at the arguments passed to the call. So let's say it's a sprintf. And it'll look to see, for example, if the first argument is a hard-coded offset to the file, or is it something that's given from outside the function. If it's given from outside the function, it's a possible format string problem there, right? So I'll do that kind of analysis. It will do control flow analysis back from the location about 64 levels and stop, and it'll try to cross-reference to see if any user supply data may be used in the same area, but it's not going to do data flow analysis step-by-step all the way down from the receive, for example. So that'll increase the chances that you have a problem, but it's, again, not going to say 100% certain whether or not you actually have an exploit on your hands. Okay, so the question is, how would you add a rule definition? It's very simple. There's a series of text files that you modify. And in there, as a number of different fields that you can set, it'll help control the static analysis. Anybody else? Yes, sir. What's been going on with rootkit.com, other than it's always up and down like a yo-yo? Well, I gave a really good class on rootkits here at Black Hat at the beginning of the week, and we covered some really neat technology, how to hide processes using eproc structures rather than system call hooks. But if you attended the class on detecting rootkits, I haven't met that fellow yet. I hope to have drinks with him tonight. He actually knows about that trick and address that in his talk. I'll just say this, there's other ways to get around all the stuff that he talked about, and I'm not going to talk to anybody about that. Those are not going to be released. Any more questions? All right, thanks guys.